Hi, this is a video presentation from Group 20.
This site visit is helpful for us to study industrial building. According to the site investigation, we got to know more about its components and how these components support each other in an individual building. For the connection of wall and roof, purlins are used to support roof sheeting and transferring the load to the ground through rafters, beams, and columns. Bracings between rafters and columns need to carry the wind load, but single bracing cannot carry the wind load from the both directions, so cross bracing should be used of single bracing in this building. For walling system, the components include columns, skirts, insulation, and bracing. For the roof systems, all the purlins are in equal space. For holding the roof sheeting in place, the appendix bucket connects rafters with bracing. We got to know the connections method as well. Pin connection for holding the truss is used in the corner of the column and the rafter, and the gray connection, usually used between column and ground. These pictures are taken from the outside of this industrial building and inside of this industrial building.
There are a few superstructure members to the industrial building entrance. This includes purlin, girts, rafter, columns, and beams. This diagram shows the different members in the framing system. Connections between members are essential as they are transferring the load from the top to the bottom. So, there are a few types of connection, which are roller connection, pin connection, and bolted connection, which are normally on sill structure. Pin connection takes up vertical and horizontal loads, but not moments, so moments are normally taken up by roller connection. There are a few loads applied to domestic shield, which are dead load, live loads, and wind loads. These are the parameters given to our group for structural members to be designed. First and foremost, wind load has to be determined. Limitation in the AS 4055, which is about wind loads, has to be considered first. Then the wind pressure can be calculated with the formula of P equals QU multiplied by CP. CP is the net coefficient for the roof general. Purlin is then designed with a selection of purlin from Lysac table. Then roll of bridging is calculated. Dead load, which includes weight of ceiling, insulation, ducting, roof sheeting, and purlin self-weight is then calculated. Live load will be calculated too as well, followed by the wind load with the wind speed at the ultimate state and serviceability state. Then calculate the load combination according to the formulas given in AS 1170, which includes downward and upward wind load. Next, determine the most critical upward and downward load combination. Then multiply both load combination with the purlin spacing to get the final pressure. Selected purlin with the span length and bridging calculated is then checked for its ultimate load capacity. Make sure the ultimate load capacity is higher than the pressure calculated. If not, another purlin will have to be selected again. When a suitable purlin is selected, the serviceability state must be checked with the wind pressure and serviceability roof support elements calculated. Then determine the most critical load combination and multiply it with the purlin spacing to get the final pressure. Lastly, make sure the load for deflection span 1 divided by 150 for ZC35030 is higher than the final pressure. Girt design will be next. Girt is a horizontal component on the wall. For girt design, wind pressure must be calculated first, when the same formula would be used. CP value is determined from the AS 4055. Dead load and live load is 0 in girt design. Then, load combination is calculated. The most critical load is determined and the ultimate state girt design is done with the suitable girt selected from the Lysac table. Check if the ultimate load capacity is lower than the capacity given in the table. Serviceability state is then checked with the wind load and load combination in the serviceability state. The most critical load is used to multiply the girt spacing to get the final pressure. The load capacity in the table must be higher than the final pressure. The next part will be bracing design. Bracing are used to hold up tensile force in the horizontal and vertical component. So in the design of bracing part, the diagonal members in compression is not considered. Here are the steps to roof bracing design. First, the wind direction either from west to east which is at the x-axis, or south to north representing the y-axis must be determined. Both the wind directions must be worked out with the same step given. The wind pressure will then be determined with the formula given, where QU is calculated with the formula stated in the slide. The wind load at the intermediate and end springs are different, so both must be calculated separately as follows. This is a roof plan with the load applied stated. The axial forces in the trusses are determined with a software called space gas. These are the forces summarized. This is a table stating the member types where compressive member will be designed with hollow sections and tensile members with equal angle, which is the diagonal members. These are the tables where design of bracing is taken from. Wall bracing design is similar. Vertical wall trusses are used to support horizontal roof trusses, so vertical bracing needs to support the horizontal bracing. There is a reaction support force at the end of both points, which is calculated in space gas. Diagonal members in compression are removed. Axial forces are determined with space gas. The diagonal members will then be designed with the use of equal angle table. All the other members will then be designed in the later stage.
We designed both intermediate rafter and the end rafter in our project. The designing rafter is a simply supported beam with uniform distributed. So the most important thing is the maximum deflection at midspan should less than the deflection limit for span for the beam. The check steps include 3 parts: design for moment capacity and compression, check for reversal action, and check for serviceability limit state. These 2 pictures are the tables used for designing rafters. This is intermediate rafter, and the supporting area is 16 square meters. The first part is designed for moment capacity and compression. In the design for moment capacity and compression, 310 universal beam 40.4 is selected, but when we check for reversal action, 310 universal beam 40.4 is not acceptable. In order to restrain the bottom flange laterally, fly bracing are needed. We design fly bracing at each purlin, but 310 universal beam 40.4 are not acceptable. So we change a heavier selection of 310 universal beam 46.2. Then we check 310 universal beam 46.2 is acceptable when bottom flange is under pressure. The final check is serviceability limit state. The deflection of 310 universal beam 46.2 is much more than the allowable limit and is not acceptable, so a bigger section is needed. At last, we use 410 universal beam 59.7 for intermediate rafter. The picture shows end rafter, and the supporting area is 30 square meters. The design method of end rafter is the same. Since end rafter has a smaller supporting area of beam, it supports a lesser dead load, wind load, and live load. So after design, a smaller and a lighter section, 360 universal beam 44.7 is used for end rafter.
In this project for bridge frame, we consider the load eccentricity as only source of moment in columns. For the column design, we usually consider the following steps. These are the steps for the basic column design. Firstly, for supporting area, which is shown as red shadow in the picture. Then move on to the dead load. It contains number of components including ceiling, installation, ducting, roof sheeting, pulling support, and rafter support. After adding this data to the design, it is necessary to calculate the maximum and minimum of dead load. For the live load, we need to refer to the AS 1170.1, table 3.2, use this equation to calculate the total live load. The wind load, we just need to use the data from previous calculation from purlin design and calculate the total wind load for both pressure and suction. According to the equations on AS 1117.0, section 4.2.2, we could use these equations to find the most adverse combination. In other words, is to find the maximum compression and tension force. To design the compression, we use the capacity table 66B with to find the suitable and economic size. And check the moment capacity. We use capacity table 5.3 to 6 to find out if the bending moment capacity is more or less than the bending moment applied. If the bending moment capacity is less than the bending moment applied, it would be okay for the design. After that, use this equation for checking capacity for combination of compression and bending moment. At last, to check tension, the capacity table 7 to 11 is required to find out if the phi nt more or less than the maximum tension. If the phi nt less than the maximum tension, it would be okay for this design. And we also need to design the end column that only need to follow the previous steps to calculate again, but use different supporting area. In conclusion, in the site visit, we knew the purpose of different components inside of the industrial building, and for the designing these members, we fully understand how to calculate these members step by step. Thanks for watching and listening.